Okay, so thank you everyone for coming to the first ACME Materials Seminar for the semester. Today we are thrilled to have Professor Matthew Pasek.
Yeah, that sounds fine.
Good, and we get an audio check as well out of that. From the School of Geosciences at the University of South Florida. Matt is a professor. He joined USF in 2009 after receiving his bachelor's at the College of William and Mary and his PhD in planetary science from the University of Alabama. His research interests are described as geochemistry, cosmochemistry, and just the scientific understanding of the origin of life. So nothing big there. So obviously we're thrilled to have you here, and I will pass it on to you with no further ado.
All right. Well, thank you, Adam. Appreciate that very much. Today I'm going to talk to you about the metamorphic effects of lightning on geomaterials and understanding the formation of fulgurites. And thank you for the kind introduction, and kind of jump into things. Of course, when we think about the changing events or things that can rapidly change materials. One that pops up occasionally, especially here in the state of Florida, is the occurrence of lightning striking materials. In Florida, the geology of the state is a little bit more bland than many other places throughout the entire rest of the United States. Consists mostly of sand and limestone, and both those things are relatively uninteresting to a metamorphic petrologist or igneous geologist, someone who cares about rocks that are not just sort of shallow marine environment. And I often tell students and things like that, that when lightning strikes sand, you can actually form the only superficial metamorphic rock that you can find in the state, and that is a rock called a fulgurite. And so a fulgurite is a rock formed by electric discharge, such as lightning, that melts the rock or soil and forms a glass that traces the heat from that discharge. So it can track the sort of lightning strike as you find it through the sand. And so some pictures here, this is a sort of a drawing that if you have ever seen fulgurites, maybe you've wandered through a rock shop and they might have them for sale at a rock shop. A well-stocked rock shop may have them, but many times you won't find them even there. And if you've watched certain movies in this game, this is Sweet Home Alabama, which is especially pertinent to this discussion. You'll see fulgurites that look like this, which look nothing like actual fulgurites. Make for pretty pictures in Hollywood pictures, but when you take a look at these things in the ground, they look a little bit more like this, sort of a lumpy gray rock with varying degrees of sort of melted, sintered material up to sort of obviously melted, and even something that looks like it might even be a little bit more vaporized in the center of this stuff. And you can see clear temperature gradations as you go across rock pebbles and things along those lines. Not quite these pretty spiral, obvious blown glass materials as shown right here. So fulgurites in general form by lightning, but definitionally or based on what people have used the term for in the literature, they don't necessarily need to form by lightning. A natural fulgurite would form by lightning, but fulgurite has also been co-opted to describe materials that formed through artificial electric discharges, such as, for instance, a down power line or a fuse blowing or something along those lines. So I should note that they're not common, but they're not especially rare. If you find a fulgurite, it's pretty cool, but is it, on par with diamonds? Well, diamonds are a little bit overblown. Is it on par with gold? No. So gold is a more rare material in general than sort of fulgurites as far as the frequency with which you can find them across all sorts of different types of materials. This shown right here is a fulgurite from Central Florida, the next county over from where I live here. It's one that formed in nearly pure silica sand, so 99.5% SiO2 in composition, and you can see that it has sort of this pattern, a long stretch of material, and a sort of a hollow center in the middle of it too. It's effectively a straw, if you will. So fulgurites have been noticed in sort of scientific literature for some amount of time. The sort of first report that we find, if we go sort of looking through books of some of the old materials, was a report by David Herman in 1711, who thought they were rocks that were growing as roots grow in the soil because they were branching out where he had discovered these things. They were first connected to lightning by Dr. Henson and by Dr. Withering. And specifically, Dr. Withering tells a story of some gentleman in the UK who saw a storm coming and went underneath a tree to sort of find cover from the rain, and then the lightning struck the tree, killed one of those people, and blew up the tree as well. And when they went to kind of investigate, they actually found fulgurites throughout the tree root where this tree had gotten struck, and where the one person had perished as a result of this lightning. And so this is the first connection between these weird branching structures and lightning forming them. And I should note that amongst fulgurite investigations, there was one famous scientist who actually investigated these rocks in South America. And that famous scientist was none other than Charles Darwin. And Charles Darwin was taking a look at a number of different fulgurites that he happened to find throughout the voyage of the Beagle, and found some strange flattened fulgurites as a result. Sort of a picture of what these things might look like is actually shown right here. You see this is kind of flat, and there's the glassy tube on this side right here. This one's from Texas, but the question was, how do these things kind of form? And it's still sort of the best sort of explanation for these things is that when the soil or sand was struck by lightning, there's probably some sort of secondary event within less than a minute or two after the lightning struck that kind of flattened and squished the glass to form a pancake from this style of material. But he was one of the few scientists of the time to give them much time of day, and investigated fulgurites as well. So when we come at this, and so I should note that I'm in a geology department, and we approach things from sort of the geological perspective. And the question we often ask in sort of intro geology is, what type of rock is a fulgurite, or any other type of rock, right? And what is limestone? Well, limestone is a sedimentary rock. What type of rock is a fulgurite? And the main three branches of petrology kind of suggest things are metamorphic, igneous, and sedimentary. And so if we were to place a fulgurite kind of in these categories definitionally, we would actually kind of fit all three of those as a definition of a fulgurite. And there is a best definition, which is that a fulgurite is a metamorphic rock. And a metamorphic rock is a rock that has experienced changes to its crystal structure, or sort of grain size, or sort of general characteristics through heating and in some cases pressure, and has formed a new type of material. So that's metamorphic is sort of the best definition. But in addition, igneous is a rock formed from molten rock, and it is very obvious in the case of a fulgurite that a molten rock, such as a molten glass, was one of the things that formed a fulgurite. And so igneous actually still fits as far as a definition is concerned. It's not the best definition, but by the sort of broad definition of an igneous rock, it still counts. And even the sedimentary rock kind of counts, because what happens in a sedimentary rock is grains of material kind of surrounding a substance freeze in those grains. And in the case of a fulgurite, grains of sand get lodged into glass and are sort of frozen in place. So a fulgurite can also be considered a sedimentary rock, but in general, we would consider them to be a metamorphic rock, which is sort of the best definition that we have. And in general, fulgurites are often considered to be pyrometamorphic, which is a pretty cool name for a metamorphic rock. Pardon me as I take a quick swig of water here. And so the fulgurite is a pyrometamorphic rock, and they're not really rocks that you would tend to kind of consider in sort of your general rock studying class or petrology class because most people don't tend to focus on these things. And a pyrometamorphic rock includes a whole bunch of different types of rock, but you can envision, for instance, sort of the generic type of pyrometamorphic rock being when lava kind of splashes out over any sort of material. It kind of rapidly heats that material underneath it and turns it into a new type of rock. So it can splash out over any sort of sedimentary rock or igneous rock or metamorphic rock. Shown here is a rock called bucite, which is sort of the stereotypical pyrometamorphic rock. And also the other thing is that these sorts of metamorphic changes tend to imply low pressure. So this is a rapid change in temperature at surface pressure of the Earth. So about 1 atmosphere of pressure, maybe a little bit more is things kind of heat up and get pressurized just through volatilization and vaporization and things like that. But in general, yeah, these things are sort of considered to be lower pressure than the average metamorphic process. The metamorphic process usually has a pressure temperature correspondence. So as you increase temperature, you also increase pressure because you're taking rocks and burying them. In this case, this is not a rock that's being buried, it's only being heated. And as a result, fulgurites are considered to be pyrometamorphic because as lightning strikes these rocks, it rapidly increases the temperature of these things and causes them to kind of freeze in a high temperature, generally low pressure style of environment. So there's a lot of science that's been done on fulgurites, especially in the last 30 some odd years. And the reason for sort of investigating fulgurites tends to be to kind of either try to get an idea of how a rapid change in temperature or energy or power, or I guess power is kind of redundant with that, a rapid change in energy or temperature of a material responds to that change. And the way these fulgurites, at least, are a pretty clear indication of a rapid style of change of material composition. And the changes that we see that occur with that include changes to petrology. Petrology is the study of rocks, which includes both minerals that are found within that rocks and the size and distribution, shape, orientation of grains within the rock, crystal structures within the rock, and sort of understanding the changes in minerals, and in addition, changes to the types and characteristics of the glass present within those materials too. In addition, there's been some recent focus. There's a paper that came out last year and one that we had, 13 years ago, that discuss how elements, specifically certain elements, are affected by being shocked by lightning. And then finally, there is some utility in understanding lightning to understand who's to blame when certain things fail. And this is a sort of forensics of fulgurite. How did a fulgurite form? Is it an act of God? For instance, the lightning strike would be considered an act of God, but from insurance purposes even. Or is it sort of a failure of some sort of man-made material? Does a power line that was poorly maintained happen to fall, strike a tree, catch fire to a forest? And then another point that I should raise here too is that we can actually use fulgurites to understand something fundamental about lightning and the sort of energy of lightning in a number of different considerations or cases. So this is sort of an outline of sort of the science of fulgurites that I'm going to present here today to give you an idea of what these things kind of look like in the field and how we can use these things to understand certain scientific questions. So sort of as the first point, finding fulgurites is not exactly easy, but it's also one of those things that tends to be, if you happen to be in the right place at the right time, you can find it pretty easily. If you're inside your house when a nice big lightning strike happens and blows a hole in the ground in your front yard, you can probably find a fulgurite there. If you're not so lucky and you want to find someplace, or if you are, I guess that depends on your definition of luck, and you want to go someplace that you can find fulgurites a little bit more easily, these are sand mines in Polk County, Florida, which is the county next to the one I live in right now at USF. And these are pure, again, pretty much pure SiO2. You can see that some of this stuff is a bit more red because of the presence of iron oxide. And there's a lot of material, very nice fine sand throughout all this material. And this is mined to produce sand for transportation industry and happens to be in a place of high lightning. And this is reports by Vaisala. Vaisala is a lightning detection firm that uses the radio frequencies of lightning in a variety of different environments. And this is a map from 1996 to 2000. Maps, of course, change over time, but you can see that the sort of the heat map of frequency of lightning strikes in various locations. And what you see is that there are places where very little lightning happens, such as Pacific coast, and other regions where lightning happens a lot more often, and including the tornado alley, if you will, right here. And in addition, places where hurricanes hit a little bit more frequently, such as the Gulf Coast or the state of Florida. In fact, the main region of Florida, called the I-4 corridor, which is where Tampa is and Orlando is and connects to the Atlantic coast, is a region where thunderstorms develop frequently. And there is a region of pink kind of right across right here that has a very high lightning strike density. And this Polk County sand mine happens to be sitting right in the middle of that, and is a great place to go to find fulgurites. And what we did is we went out to this location. And okay, so here's another map showing sort of the global distribution of lightning throughout the sort of surface of the Earth. And what you have here is a high area of lightning in Florida and that, but there are other places where lightning is even more common, such as the Congo. So lightning it's not to say that Florida is the lightning capital of the world, but it's lightning capital of the US. Although I have heard that due to some changing climate indicators 2 years ago, I think Oklahoma took over the mantle for at least a year versus Florida. We had a quiet storm year that year, and Oklahoma had a very bad one. But in contrast, you see that the U.S. is not quite as lightning heavy as some other places in the U.S. You also see that there are places where lightning is very minimal. Most lightning occurs over continental landmass. In contrast, lightning is not too common over the ocean. And there are, of course, other places where you can induce lightning changes, such as this is a volcano kind of expelling material, and you see some nice sparks discharges there too. Dr. Genero, for instance, studies the process that volcanic lightning forms or alters materials in these places. There is also the most recent volcanic explosion in Tonga, for instance, also had some very beautiful pictures of volcanic lightning happening there too. So there are places that lightning will occur that can actually alter material in those environments as well. And let's run one more time just for the sake of completion. But it is most lightning kind of forms as a result of thunderstorms. However, there are other places that it can form as well. So the formation of a fulgurite tends to be accompanied by a strike of lightning. Lightning is very hot, as you know, right? So lightning is about 25,000 Kelvin, which corresponds to about 4 or 5 times hotter than the surface of the sun. So very hot material. Because it's so hot, nothing is a solid at the point, nothing is even a liquid, and many things aren't even gases. So it vaporizes. Lightning, as it travels through a material, will vaporize solids, turn some material into plasma, and this occurs over the course of less than a second. A lightning strike is a very rapid phenomenon. And the main amount of energy that is deposited into the ground actually occurs over even less than a second, even on the order of milliseconds or even possibly microseconds is where you get the bulk of the energy. You can actually track the energy of lightning based on the size of fulgurites. And we did this in 2016, where we took a look at a bunch of different fulgurites to kind of track how lightning and energy is distributed across a number of different samples. So giving that perspective of what kind of happens if you have a lightning strike, sort of as shown in the schematic, and you have a non-conducting layer, for instance, sand or soil, and then you have a conducting layer. The lightning is trying to dissipate by reaching this conducting layer and will travel through the soil or sand, melting and fusing and vaporizing this stuff, and then will dissipate sort of in this conducting layer and leave you with a tube of material called the fulgurite. Again, this is the picture of that fulgurite to show you roughly what it looks like. Again, great temperature profile here of sort of a cooler, but still pretty hot outer crust, followed by sort of a bubbly sort of transition zone, and then a melt zone, and then finally a central void. And the central void is where the rocks and materials were actually vaporized during the lightning strike. And you can imagine lightning is going straight through here, and you can track sort of the energy of a lightning strike based on how big this void is. A larger, more energetic lightning strike should result in a larger amount of material vaporized. So at this mine in Polk County, Florida, we collected about 270 fulgurites or so, and we measured the size in terms of length and the diameter of each and every one of these. And what we did, because we could not get each and every single fulgurite in full, because this is an active mine, a lot of material is being mined and cracked in half. What we did was we measured the average diameter, and then we're able to trace that into an energy per unit length. And see that fulgurites vary in size from sort of wider to thinner, but some of them are long, some of them are not. This is what they kind of look like if you're to go to the field and hunt for these things out. You have a nice the central void in the center, and then you have the glassy tube going down, and this one's sticking out of the ground. It was an actual one that we collected from this mine to take a look in person to collect. And give you perspective where this is at. This is the mountain range of Florida called the Lake Wales Ridge, where it reaches a nice height of about 200 feet above sea level at its highest point, which is also the highest point in Florida, which is pretty pitiful, but that's Florida for you. And the Lake Wales Ridge is shown right here. There are other higher points as well, and these things, as you see them, are a sand dune that was probably aeolian or wind-based that kind of collected sand and then got struck by lightning over the course of a couple million years. This is an older sand dune. This is a sand dune that's not been inundated in the last few million years rather, and has been sort of above ground for some length of time. And so again, in order to measure the energy, we're taking the various diameters of fulgurites. Larger diameters mean larger energy per unit length of these things. And we graph these as sort of a frequency profile. And what you have here is the log of the energy in terms of megajoules per meter. And so the energy required to vaporize the amount of sand in the interior can determine the energy in terms of megajoules per meter, again, based on the length of these things. And you see about the 50% point. It says that the average energy in terms of megajoules per meter is that a lightning strike, as it deposits energy into the sand, will be on the order of 1.2 megajoules per meter. And that's a fair bit of energy. That's a lot of energy. And there are some lightning strikes that are even heavier. This one right here would be about 25 megajoules per meter. So that's a rather large energy strike. And there is actually, if you instead of doing a distribution diagram, you can do a sort of bell curve. This follows a bell curve in log normal space. So the energy logarithm of the energy space, it follows a normal distribution from there. And if you don't like this megajoules per meter, we've also shown that the megajoules times the length of this material also follows a similar trend. And the average in that case is on the order of a little bit less. The average length of a fulgurite is about 10 centimeters. So about a tenth of that, on the order of a couple, maybe 100 kilojoules or so for the average formation. So there's a lot of energy that's being deposited. And if you take this, of course, you can kind of combine this with the petrology, the ultimate formation, how the rock changes with this material. So the types of rocks that get changed by lightning, they differ in terms of blockiness, glassiness, material, and void space. And in 2012, we took all these different types of rocks and divided them according to sort of these various trends. And you see that some are pretty much all glass, and some are very little glass, but very dense. And the most common fulgurites we tend to find, all these ones from Polk County are called type 1 fulgurites. They're these thin quartz SiO2-rich fulgurites, and then there's some that are more glassy, clayey materials, and then there's some weird ones that are sort of more calcium carbonate rich. And the sort of dynamics of how lightning strikes these materials kind of informs some of what sort of fulgurite you get as a result of these things. However, there's some pretty ones too. This is an exogenic fulgurite. This is what happens when a lightning strikes a soil and then a droplet of something kind of splashes out. And you can see sort of the droplet style structure of this thing. This one is associated with a fulgurite from Utah, and it's got some nice bottle green glass on it. These things are not divided off of sort of the main 4 types of fulgurites, but are sort of associated with these things. They are morphologically different, compositionally just slightly different, but they are associated with those styles of fulgurites too. Now, I will note that when we started investigating these things, the people who have looked at fulgurites before included Eric Assine and Dave Fisher, and they presented in 1986 that there's some strange minerals that had never been seen on the surface of the Earth before that were made of iron silicon materials, or iron silicon minerals, rather. They are minerals consisting of Fe and Si only. And these were reported in a fulgurite from Michigan and had never really been found in nature before. But since then, there have been many more occurrences. Several of them have been associated with sort of strange lithologies that we find in China, for instance, or some of them have been found and are proposed to be associated with impact craters. But there's some open questions as to what those formations are. We have a review that just came out last month, in fact, that described these weird iron silicon minerals that we find in fulgurites. But there are many others who have looked at these things. These are sort of magnets for interested mineralogists. And a lot of the work on fulgurites has been done by mineralogists who find crazy minerals in fulgurites. They're like, hey, how does this form? Where is it from? What is it? What's its distribution? And so, for instance, Christian Stefano in 2020 presented some work on these things. And there's been work by groups in Mexico who have looked at fulgurites from Mexico, finding these iron silicides. So to give you an idea of what these things kind of look like, this is a fulgurite from York County, Pennsylvania. It's actually an exogenic fulgurite. This is a 3-color map where red is iron, green is aluminum, blue is silicon. And you note that the majority of this thing is kind of this blue-green color. It's mostly aluminosilicate material, but there are these blobs of sort of purple color, which is actually iron and silicon in it. Now let's take a look at this one right here. And we're rotating at 180 degrees. And when we took a look at this thing, it was actually pretty unusual. It is an iron material. And when we looked in close at this thing, we found that there's some very interesting texture of this material. And there's the composition of the dark material was actually FeSi. So it's about 1-to-1. This is an atomic amounts of material, atomic ratios of material. So 50.5 and 49.5 Si. So this was 1-to-1 FeSi. And then there's this other material in here too, which happened to correspond to about 60-40 Fe to Si. And so it's a 5-to-3 ratio or thereabouts. So there are these weird FeSi minerals that we have found in fulgurites on our own as well. But these things are sort of the main draw for why we are kind of curious about these things. Because when we find these weird minerals, a mineralogist is like, hey, let me take a look at that more in depth and figure out how that forms. And there are parallels with the formation of these materials to, for instance, impact craters, extraterrestrial rocks such as meteorites also have materials like these, and they're not common beyond these weird occurrences in fulgurites or these other strange places we happen to occasionally find them on the surface of the Earth. In addition to kind of changing the composition of certain minerals, making these weird iron silicides, there's a number of other possible changes that can occur during lightning strikes. Lightning is identified as one of the few ways of fixating nitrogen. So it takes nitrogen, which is N2, and can, when it strikes when lightning strikes the atmosphere or travels through the atmosphere, you can actually make nitrogen oxides, such as nitrates, and thereby also reach ammonia from some of these processes. And that's viewed as one of the ways of restoring nitrogen to the sort of soil, allowing plants to kind of use it and uptake this element, which is critical for all sorts of biology, but does it affect other elements? And our first work on fulgurites, again, came out 13 years ago, oh my goodness, and discussed how lightning affects redox chemistry of the element phosphorus. And this is a nice fulgurite shown right here. This is actually a glassy plug that filled up the tube of a fulgurite from Greensboro, North Carolina. And is very happy that this paper in 2009 got accepted in Nature Geoscience, and then also made the cover art as well, which is a lot of fun. Helped secure a job when I was hunting for one as an assistant professor. And what we took a look at with this fulgurite were the presence of weird phosphorus compounds such as phosphites and phosphides. And a phosphite is similar to a phosphate, but there's an ite instead of an ate, and a phosphide is a lot more different. And what we estimated was lightning is capable of reducing around about 3,000 kilograms of phosphorus every year. And this is not by any means a large amount, but it is a route to forming reduced or changing the chemistry of phosphorus, which is otherwise pretty intractable to sort of environmental changes. Giving a perspective of what this kind of looks like, this is a fulgurite from La Paz, Arizona. And what we finally did was we found a phosphorus carrier that looks kind of like this. We actually don't know very much about this thing. It's rather hard to sort of investigate using the typical means that we have. This is a backscattered electron image from microprobe. And unfortunately, the size of these materials is too small to get a good analysis on by microprobe. But when we took bulk extracts of the rock, instead of phosphate, we found phosphite. And a phosphite is one in which the oxygen of a phosphate has been replaced by a hydrogen. And this is, if you put that an oxygen right there instead of a hydrogen, you would have a phosphate. And this was the first occurrence of phosphite found in natural terrestrial samples, which is why we were able to get the paper that we did. In addition, there are other places that we found some phosphides, and these are grains of phosphides. In this case, imagine the iron silicide being FeSi. This is sort of FeP. There's no oxygen bound to this material. And these grains of small metallic material were actually iron phosphide. In this case here, a 3-to-1 ratio of iron to phosphorus, and had a parallel in a meteoric material called schreibersite. And format for schreibersite is an iron nickel phosphide. In meteorites, nickel is more common. In fulgurites, the nickel is pretty rare. And so this was the first occurrence of non-phosphate found in superficial rocks, and it was formed by lightning. May be relevant to sort of forming new minerals and to sort of affecting the biological cycle of phosphorus. And there's a paper that came out last year that investigated this fulgurite right here from Iowa, that they found a weird schreibersite mineral. We did not find schreibersite in this previous sample because the rocks are too small, or these grains of metal are too small to see these sorts of things. But in this rock right here, the material is definitively identified as the phase schreibersite, which is pretty much exclusively found in meteorites. So there's a parallel between impactites and lightning strikes and meteorites that we see in these different types of rocks. Now, jumping sort of material or jumping subject areas here a little bit, let's consider the power of a lightning strike. I've already given you sort of a scale of the energy of lightning, and we know that the energy scale of a lightning strike is on the order of about a megajoule. Maybe a little bit less, but not that much less. And I've noted as well that this is deposited in a time scale on the order of a microsecond to a millisecond. Take this megajoule and divide it by a millisecond is sort of the units here. The power is on the order of gigawatts, and that's a lot. And you can think of the famous use of lightning by Back to the Future, where he's like, how do you get 1.2, well, in his case, he says gigawatts, but it's gigawatts of power. And they end up using lightning to send the DeLorean back to the future in that way right there. And that's actually pretty close. 1 divided by 0.001 is on the order of a gigawatt. So it actually works quite well. So the interesting thing is that this very high power means that lightning is shocking. I use that in sort of a pun sense here, but it is actually a process of that we identify in geology called shock metamorphism. And so one of the biggest surprises of fulgurite mineralogy is that there is some amount of shock metamorphism of quartz, where we have here on the left-hand side are Raman images of quartz that actually shows some indication of shock based on sort of the alteration of some of these main peaks that we find in a Raman spectrum. And this is presented by my colleague Elizabeth Carter 12 years ago, and has been looked at separately through other means by Enda and Gary in 2017, and pretty conclusively shows that there is some amount of shock that occurs in a lightning strike to the rock that gets shocked. And so these are important to understanding the geologic impact record, because the presence of shock minerals has been used sort of as a definitive identifier of an impact. But is that the case? Well, we did some modeling, my colleagues did some modeling of how lightning would shock a rock. And what you have here is sort of the microsecond time scale that shows that as a lightning strikes a rock, you can get a very high initial pressure on the order of gigapascals. And then this propagates outward in the type of rock and sort of shocks it and drives a very high pressure front that sort of is followed by sort of an alteration of the minerals as this pressure shock reverberates through the soil or sand that gets struck. And so the peak pressures sort of outside the zone of melting are on the order possibly of 10 to 20 gigapascals. This ends up kind of really affecting quartz mineralogy. This is a grain of toasted quartz, kind of. It's kind of like a quartz has obviously been stressed by heating. And it can also make something called diaplectic glass, which is a type of glass that preserves the original texture of the mineral that it formed from. In this case right here, this is a quartz glass, quartz right here, and SiO2 glass on the downside of this. And it's a grain of quartz that kind of got half melted and remains still in situ right here too. Similar to the effects on quartz, there are some interesting effects on zircon as well. And zircon is a mineral called, it has a formula ZrSiO4, and it's not exactly a major rock forming element, or a major rock forming mineral, but it is found throughout a number of different types of soils and sands as a trace mineral. And what we found is that when zircon gets struck by lightning, it forms a mineral called bedelite, which is ZrO2, zircon oxide, and releases SiO2 to kind of go off into the environment. So what other effects does lightning have on rocks, and how does this differ from an impact? And this is a paper that came out just last year on the effects of lightning on zircons. And my colleague, Gavin Kenny, working in Sweden, took one of my fulgurites, this one here is from York County, Pennsylvania, and sort of mapped the different forms of zircons that were found in this fulgurite. And what you have here is the central void. The central void is where the peak temperatures are sort of experienced in this fulgurite. And then you have sort of a thermal profile. The temperatures decrease radially outward from this very hot center right here. And you see that there's some zircons that have zircon bedelite rims, zircon oxide rims. And those are sort of right next to the central void, which is something you might expect. And then they are progressively less altered by temperature as you kind of go radially outward from the central void. I'll give you a picture of what these kind of look like. This, again, is a backscattered electron image of a zircon, which is right here. And you see this kind of weird looking sort of outer rind of the zircon, which is a ZrO2 rim, the bedelite rim. And then as you go a little bit further out in the glass, you have things that are still being altered, but not necessarily completely changed. And then you have the unaffected zircons on the sort of farthest out material as well. And using some of the magical techniques that they had to kind of analyze these things, you can actually track what types of minerals there are in these things. And it turns out there's both cubic and monoclinic ZrO2 zirconia resulting from this thing. So cubic zirconia you probably have heard of as being a diamond simulant, but there's also monoclinic zirconia as well, or zircon oxide that can be found in these materials. And these things actually have been used as impact identifiers. Turns out lightning can form them just the same as well. In addition to these strange effects on minerals, there are some strange effects on the glasses as well. And in 2019, we investigated a blue fulgurite from Marquette, Michigan, which is a sky blue to a darker blue shown in this picture right here, trying to figure out why this fulgurite was blue. Turns out, again, drawing on the parallels between lightning and impact, the only other place that a blue glass like this has been found is in Zhaminshin crater in Kazakhstan. And so what are the parallels between Zhaminshin crater and the origin of this blue fulgurite that is otherwise, coming from Michigan for some strange reason? And the origin of this blue color actually is not a compositional effect, but is a material effect. And within this fulgurite, there are tiny spheres of silica-rich material. So this is all these spheres, as you see right here. This is a nice silica sphere, and this is a map done by TEM here, which has some compositional analysis. And we see the hole in the center is actually, this is a elemental map. Blue is SiO2, and then other elements such as Fe and Al are other colors here. And you see that this center here is actually SiO2. And these grains happen to be of the correct size to permit Rayleigh scattering. And what you have in the blue effect is actually similar to the blue effect of, say, blue spring water or other things, where tiny spheres are sort of refracting light just so and are giving this nice blue fulgurite its brilliant blue color. So to conclude sort of the science of fulgurites, I also want to talk a little bit about the forensics of fulgurites. And our definition of a fulgurite is a rock formed by electric discharge, such as lightning, that melts this rock or soil, and when cooled forms a glass. And are there other discharges? The answer is yes. This is a rather obvious case of a different type of discharge. This is a downed power line. Due to human sort of power demands and needs, there are electrical lines that have huge amounts of energy capability. And so a down power line can release a lot of energy over a much longer period of time than a lightning strike. And sometimes you see some pretty obvious materials that have been affected by man-made material. This is a fulgurite from Tucson, Arizona, that is made completely of aluminum. And where did this aluminum come from? Well, it turns out that the two main conductors in power lines are either copper or aluminum. This is an aluminum power line that sat on the ground for a while, melted and formed, melted and got some silica glasses, some various glasses kind of splattered throughout it and formed a nice blob of aluminum, complete with lumps of glass inside of it too. We also see other types of conductor. You see this nice copper colored material here and even this green material here. These are power lines, copper power lines that are the source of the discharge that a fulgurite kind of builds itself around. So there are very clearly effects of lightning that can be quite important for understanding the origin of a lightning strike or understanding the origin of a fulgurite. And the reasons why this matters is that sometimes there are people want to find out who is to blame for certain things. So there was a forest fire in Wyoming in 2006 that was traced to a point close to a power line operated by a power company out there, and they found a fulgurite. And they're curious, what is this origin of fulgurite? What does it mean for the distribution of the, what does it mean for who's to blame or to fault for this forest fire? And based on the forensics of this rock, this fulgurite, the question was, can we sue the power company for this thing, or is this a naturally formed lightning strike forest fire, in which case it's not the power company's fault? And there are about $100 million at stake for this lawsuit, so it's a very expensive lawsuit. That's a lot larger than most of the budgets for various NSF programs, for instance. So it is a financially important relevance to this thing too. So you can actually track the origin of fulgurite based on some of the minerals that are present within that fulgurite. And for instance, in this case right here, what we have is a map of a fulgurite that sort of is a artificial fulgurite in this case. A little bit further on is a nice grain of aluminum from a conductor. And what you have is a band in Raman. There's a Raman band associated with quartz that is slowly replaced by a mineral called cristobalite, which is a low pressure, high temperature SiO2 form. And it turns out that cristobalite actually requires about a couple minutes to form. So a shock by a power line can form cristobalite, but cristobalite is not usually associated with a lightning strike because the time scale of formation of that mineral is too small for it to sort of form on the rather rapid cooling time scale of a fulgurite. So this is a paper we have out in Mineralogy and Petrology that argues that you can actually start tracing the origin of a fulgurite based on some of the minerals that you find within it. So to summarize, fulgurites are an unusual rock representing conditions not usually encountered in sort of your average geological sample. And hence they're kind of an unusual and interesting material. I have a book that is available on Amazon if you're curious to kind of follow along and see these things. Not trying to hawk my book or anything like that, but some of the points I raised here kind of in there too, and there's some nice pictures in as well. Some of the ones I've shown throughout this thing right here. So to say thanks, I'd like to thank all of my collaborators and colleagues working on this thing, from Tian Feng, who's done the most recent work, and Gavin Kenny and I have tried to figure out the Zircon stuff, and some grad students and local geologists who helped me get onto places to look for things, and as well as NASA for support from Emerging Worlds and Exobiology. So with that, I can end and take any questions.